Hey guys, this lesson is on the integrated rate laws. This particular aspect of kinetics allows us to answer the question, well, if a reaction, and we'll take a very simple one, A reacting to form B, proceeds after a given amount of time, how much of A is left over at that time, and conversely, how much of B has been produced? Nothing that we've done to this point, whether it's the rate expression or the rate law, allow us to actually answer that question. The question of, after time X has passed, how much of each of these two things do I have? Well, depending on the rate order, you approach it a different way. Which rate law, integrated rate law you use depends on whether or not your reaction is a first order, second order, third order, zero order reaction. Let's take the first order reaction as an example. If you know that it is a first order reaction overall, then we're going to use the integrated rate law of ln, the natural log of the concentration of A naught divided by the concentration of A at time t is equal to K times T. This is, of course, as I said before, if it is a first order rate law. Now, the calculus you need to do to get to this integrated rate law is sort of beyond the scope of this class. It's not a calc-based class. So you just have to learn to memorize this formula. What do each of these terms mean? Well, A naught, whenever you see a naught like this, that's a subscript 0 in this case, that's referring to the initial concentration of A when you started the reaction. And A at time t refers to the time. Let's say you want to know how much of A remains after 2 minutes. Usually it's expressed in seconds, so you would use your information, plug and chug, at a time of 220 seconds. If, for example, you have a second order rate law, then you would use 1 over the concentration of A at time t is equal to, I'm sorry, that's wrong, it's minus 1 over A naught, the initial concentration of A, is equal to KT. If it is a zero order reaction, we use the rate law, the integrated rate law of A at time t minus A naught is equal to minus KT. So these three expressions, zero order, first order, and second order, these are known as the integrated rate laws. Unfortunately, you just have to memorize them for the test. One way in which they're applied might be, for example, radioactive decay. Radioactive decay is an example where it's a first order reaction, and you can use this information to determine how much of the original radioactive substance you have left at time t. In a situation like that, you're most likely solving for what is the concentration of A at time t. In another video, we will explore the application of these. But for now, we're just going to look a little bit more closely at these themselves. If you look at these different expressions, one of the things you'll notice is that graphing the original data can lead you to which of these you might use. If we're looking at the first order reaction, the natural log of A naught divided by A at time t is equal to KT. If you graph the natural log of A sub t over time, you get a straight line. whose slope is equal to minus k. The y-intercept is equal to ln of a naught. The reason this is true is if we expand the expression as it's written above, what we find is ln of a naught divided by the ln, divided by the natural log of a at times t. We can expand that. And so we take that part of the first of the integrated rate law and we write it as ln of a naught minus ln, of a at times t is equal to kt. ln at is equal to minus kt plus ln at a naught. And if you think about the equation for a line, right, y is equal to mx plus b. Y here is the natural log of A's concentration. The m is the slope, which is k, and the y-intercept is ln of a naught. So if you graph this data, if you graph the natural log of a at time t versus t, you get a straight line. And if we look at the others in a similar fashion, what you would notice is that if you have a second order reaction, 1 over a at times t versus t gives you the following. And then the y-intercept here is 1 over a naught. And then if we have a zero order reaction, a at times t versus t, our y-intercept is a naught, and the slope, m, is equal to minus k. So by graphing your data, either as ln of a at times t, or 1 over a at times t, or a at times t versus t, one of these three should appear. And if you have a straight line for ln of a at times t versus t, it's a first order reaction. If you get a straight line when you graph it this way, with 1 over a at times t versus t, it's a second order reaction. And if you get the straight line when you graph a at times t versus t, it will be a zero order reaction. You would never be able or expected to do this on the AP, but what you would be expected to do is to recognize which of these gives you a straight line based on the integrated rate laws. This is how we end. Another way to get t or k, by the way. You can get k from these slopes, in addition to the way that we talked about earlier. So these are the integrated rate laws. You do need to memorize these, and you do need to have these at your disposal during the AP. The next video we'll do explores how to apply them. But for now, here are your integrated rate laws.